मैंने फोन. So which one are you talking about in the Midsem paper? Okay. Okay. So have any particular doubt or you want to explain this one? Hmm. Hmm. Yeah. Yeah. The cost, you can think of reward as minus of n minus 2. Right? So maybe it's the cost, it's not the reward. Minus of that will be reward. Okay. Let me see that. Okay. This one. So you're starting at some stage. Okay. You're starting here, and with some probability p, your food will be available, and with some probability 1 minus p, your food won't be available. And the actions here, if there is no food available, there is nothing much to choose. You have only one action, which is don't buy. And this is okay, right? That transition is okay, right? If it, like, the cost will be zero, right? Because so right now, there is zero cost because you haven't carried anything till now. For how many steps you carried the food is the cost, right? So if you don't buy in the first step, then there is no cost in that step. So if you decide, in this case, you have two options. If the food is available in the first store, you have two options. One is to buy, one is not to buy. So if you buy, you have, uh, that is not one. That one is not the reward. That one is probability. With probability one, you will go to terminal state. Like, those are the probabilities. Yeah, the reward is, we are just writing cost. We are not writing reward. So if you choose to buy, the cost will be n minus one, right? Because for n minus one steps, you have to carry that food, right? If you choose not to buy, then you won't have any cost at that time. So again, you will go into two possible states, which is available, not available, and so on. So for those who are not familiar with the problem, this is the problem. Like, you are walking across a line of stores, and you are interested in some particular food, and you don't know in which store the food will be available. So you are walking across all the stores one by one. So, like, if you buy the food in the first slot, in the first stall itself, let's say your like food is there in the first slot itself. If you buy that, you have to carry that food for remaining n minus one steps. So the cost will be n minus one. But if you buy the food in the last shop, then you will have just the cost of one or zero. But the problem is, if you don't know whether the food which you are interested will be available in that shop or not, right? So it's a trade-off, right? If right now you find the food which is of interest for you, but whether you can skip buying that and take the risk of going to the next store in the anticipation that you can save some cost of carrying the food, with the hope that you will find your food in next store as well. So the question is to model this as an MDP. And in every store, the probability of finding the food which is of interest to you is with some probability P. At some probability 1 minus P, the food which you want will not be available. Okay. Okay. Argue that if it is optimal to buy at store A when the item you like is available, then it is optimal to buy at store K plus 1 when likable food is available there. Okay. So if you buy the food at if your optimal policy says to buy the food at let's say if it is there, like only action is if it is there only, if the food is which is of interest for you, if it is available, then only you have to take some decision, right? If it's not available, there is nothing to decide. So if you're talking about a deterministic policy, so let's say which says the policy says that if the food is available at the Kate store, if the policy is asking you to buy that food, okay, then that policy, it does not make sense to say if it is available at K plus 1 store, don't buy that, because you are ready to incur a cost of n minus k, right? If it is available, you are ready to buy at K store, right? Let's say it is not available at that time. In the Kate store, you have decided if it is available, you will buy. But in the Kate store, it is not available. In K plus 1 store, it's very logical to buy that, right? If it is available. Like if you think logically, uh, if you already decided that at 10 store, I'll buy if it is available. Then if it is not available at 10 store, if it is available at the 11th store, you'll naturally buy that. So any optimal policy will have this kind of a property that buy at any shop greater than or equal to 10. Right? So that is one logical thing which you can argue. That's one property which we are trying to tell. Yeah, because an optimal policy will not have this kind of a character. If it is available at 10th, you buy, but at 11th, you don't buy. At 12th, you again you can buy. So it does not have an optimal. Like intuitively, the optimal policy will not have such a structure, right? Because when you are ready to buy, incur a loss of let's say n minus 10, then n minus 11 is also good enough. So the other things will be more or less trivial, I think. If you agree with this slot, with this uh, property, find the value function of a policy that does not buy till n minus 1 and stalls and buys only if it is available in the nth stall. This will be trivial, I think, because from the diagram of the MDP, you can find this. And you are doing it iteratively to get the general policy. So this MDP, you understood, right? The MDP is like, once I explain you the MDP, it's very trivial to understand that it's a valid MDP. But if I'm asking you to write the MDP, coming up with this idea is a little tricky, because you have to be very clear about what will be your states. Like here, I have nicely written one not available. Maybe if you have just taken one as a state, stall one as a state, maybe you would not have understood what actions will be there and how to draw the MDP, right? So, like, you have to have that clarity on what will be my state, because it's not very intuitive. Like, just by looking at the problem, you will not guess these will be the states. Once I tell you these are the states, then drawing the diagram may be easy. I'm writing cost, right? You can think reward as minus of that. Like in the grid problem, we take minus one reward for every step, right? So just like we can, instead of that, I can say cost is one. So I can just think of cost as minus of reward. So instead of cost, I can call it reward of minus n minus one. This is a terminology. No, we won't visit, right? Like you will just pass through the. Like you imagine that you are passing through some airport. So you are going to terminal state, right? Actually, you are going to terminal state. Yeah. Mm, yeah. No, it's not about going to store one. It's like you're checking. You imagine like you're walking in some corridor where the stores are there, like yes, sequence. You're just checking through the stores and going. You're checking all the stores. So imagine that you want to buy, right? They're they're just going across that corridor by looking at one shop of the other. Even if you visit shop one, in this shop you need to find the product. You don't know beforehand. And we are visiting by default. It's like you don't think of visiting as an action. You just think like maybe some yeah, some people are sitting in the corridor. Oh, okay, anyway, so uh, uh, maybe this time I'll try to be more elaborate. No problem. And don't worry about that. Yeah. But at least that's what the problem is. You are passing through some sequence of stores, and at every store the product might be there with some property. It might not be there with some property. If it is there, whether you should buy it or if you because if you buy it you'll have to carry it for the rest of the distance, so the decision is whether it's you want to buy it or you want to take a risk thinking that it might be available in some other store as well, so that my cost will be less. Okay, estimate. Where is it? So value function of a policy which doesn't buy till n minus one stores and buys only at the n store. This is like the threshold policy, as I said. Hmm. V pi of V pi n comma available is like these are the states which we have, right? Okay, let me try to recollect notation. This notation is fine, right? V pi of s, where s is of this form, and if you buy at the last store, you don't have to carry it further, so your cost is zero. So that means your total cost is zero. And what is V pi n of it is not available? So this is, I think this was mentioned in the question, right? You'll have to pay that much if you don't have the product at all with you. Like if you miss the product in all the stores, you have to pay terminal cost of this much, right? This is fine. And this is this one you're talking about. V pi n of n minus one comma available. So what does that mean? So this is V pi of s for some state, right? I'm just using the uh, uh, Bellman expectation equation, right? This is Bellman expectation equation. Now, what is it you're asking? No, I'm not saying this is zero. I'm saying this is zero because immediately you're not getting any cost, right? for not buying. If you buy for every store, you have to like you have to carry, right? You'll get minus one cost, one cost for every step. If you don't choose to buy, you only get the cost at this place, right? One minus P cost. Yeah, that's the state, right? You are in the state one n minus one, and it's available. But what does your policy say? Pi n policy, right? What does pi n policy say? So that means according if you follow policy pi n, you are not buying at store n minus one. So the immediate cost that you'll get will be zero. Yeah, right. Because this is also cost only, right? Mm, right. So this is fine, right? R pi s will be zero because if you follow that policy pi, at this state you won't incur any cost. If at all you incur cost, that cost will be finally if the item is not available at the nth store, then you'll incur this one minus this cost, like like this cost one by one minus p cost. And if it is available at the nth store, then the cost is zero. With some probability p, the cost will be zero. With some probability one minus p, your cost will be this much. So this will be your cost for this state. Fine. Okay. Question three of this midsem. Which among the following is or are the differences between contextual bandits and full RL problem? Like contextual bandits can also be modeled as an MDP, right? You can just think we modeled bandit problem as an MDP, right? Once, like you only once, like you have, like in contextual bandits, like there will be multiple states, and when you are in some state, uh, you can have multiple actions possible, right? So there will be a lot of states, like let's say based on the user features, every user is like a state, right? Let's say there are two user features, let's say age and let's say gender. So let's say I'm discretizing these states. Let's say age is either older or younger, let's say, and gender is let's say male or female. So now I have four states based on the user's features, right? User feature is the state, right, in contextual bandits. So my states will be what? Old and male, old and female, young and male, and young and female. Okay. My actions will be, let's say there are two articles to show for me. Like for every user, there are two articles which I can show. So there will be some two states, two actions which are possible for each of the states. And if you show some article to a user, what will happen? He will get either he or she will like the article or they won't like the article. So you'll take, let's say there are two news articles, news article one and news article two. You will just show one of these two to whatever state you are in. Then if the user likes, you will get let's say plus one reward. Otherwise, let's say you get minus one reward or zero reward. Then what will happen? This episode will terminate. It's not like you will go from this state to another state. So that will not happen, but you can model some terminal state saying that like depending on the action, he will go to whatever action he takes, he'll definitely go to terminal state with probability one, and the reward will depend on the action. So you can model it as an MDP. That's not an issue. Any other have any doubts in this? Someone has a question four. Huh? Okay, I'll come to that. So what is this? Okay. So what is the doubt? Yeah. Why? If gamma is 1, what is the P2 telling? So if P2 is a policy, then what will we have? Good, you're saying? No, what do you mean by better policy? No, better policy is not more reward, right? Here, what are we trying to do? We are trying to frame the shortest path problem as an MDP, right? You want to frame the shortest path problem as an MDP, right? Whatever your aim is to make sure that the optimal policy in your MDP will lead to the shortest path, right? If you model with gamma equal to 1 in this, what will the optimal policy be? Just wander around anywhere without going to the uh, like whenever you go to the terminal state, you'll get a reward of +1. In between, you don't get any negative reward, right? You get zero reward. So whether you wander around for some 1,000 steps in the grid and then go to the terminal state, your total return is what? +1. Whether you go in the shortest path, then also your reward total return is +1. So you are not learning the shortest path through this MDP, right? But if you have a gamma equal to, let's say, 0.9, then what will happen? If you reach the goal in, let's say, 10 steps, your total return will be what? Like you will get 0 plus 0 plus 0 plus so on. In the 10th step, you will get uh, gamma power 10 into zero point 0.9, right? This will be your return, right? What is the return? Like GT is RT plus 1 plus, like if I talk about G naught will be R naught plus gamma power 1 into R1 plus gamma square into R2 plus on gamma power 9 into, let's say, R10, right? So if you reach the goal in 10 steps, all these rewards will be 0. This will be 1. So you'll get a return of gamma power 9, right? So that means if you reach the goal after n steps, your return will be gamma power n. So that is diminishing with the return is decreasing with the number of steps you took to reach the goal, right? So that means if you have a gamma which is less than 1, your optimal policy in your MDP will be the shortest path. Because if you go in any other path, your return will be lesser. But if you keep gamma equal to 1, in whatever path you reach to the terminal state, your return is 1. Because gamma power 9 will be 1, right? So there is no incentive for the agent to reach the goal in the shortest path. That means there is nothing that it is learning, right? Yeah, any other doubts in the midsem part? Okay, okay. So suppose we want an RL agent to learn the play of fire. I think I wrote something right here. Like this is the way to argue. Like if you give an intermediate reward, like the question is, if you give an intermediate reward for being away from, if you are close to the goal, if you give some reward, let's say, then there is no incentive for it to reach the goal, right? Let's say it keeps circling like in a circle. Let's say you have some goal here. If you, hmm, yeah, no, that's not the question, right? Given an MDP, what is considered as an optimal policy? The one which has the highest return, right? Like just circling around this is also a policy, right? A deterministic policy. You keep circling around the goal, let's say at that 1 meter distance, then what will be your return? Infinite. So once you model the MDP, I'll do value iteration and find the optimal policy. So the value iteration will give me this policy because the value iteration will find the optimal policy, right? So this is the optimal policy for that MDP structure, right? Because what is optimal policy? The one which will give you the maximum return. So what is the use of going into the goal? The episode will terminate and I'll get plus 10. Yeah. So if I keep circling around the goal at 1 meter distance, then I'll keep getting plus 3, plus 3, plus 3. So that will be the optimal policy. So that is actually hindering your aim of going to the goal. Yeah. No, we are not saying that this is the best MDP. The question is whether I think deciding which is the optimal MDP maybe has a more broader problem, but at least this much is clear. So that I don't know if there is a definition of what is an optimal MDP. Right? Given an MDP, we know what is an optimal policy. So if you have some problem of I want to reach the goal in the shortest path, you model it as an MDP and come up with the optimal formulation of MDP means I don't know what it is, right? Because there is no such definition of what is the optimal MDP formulation for some real-time problem, right? You are just trying out some MDPs which you think are meaningful. Okay. So any other questions? And, hmm. Yeah, that's why I wrote this is an optimal policy. There will be multiple optimal policies. So here I wrote, right, this is one example policy that can achieve the goal from any. Hmm? Hmm. Did I write that anywhere? Yeah, this is that, right? As discussed earlier, an optimal policy should avoid these two should avoid these two things. Any policy which avoids those two will be an optimal policy. Like the main thing here is if you try to go up in this, if you try to go up in this uh, cell, uh, there is some probability of going into the hole, right? Because of this wind, like there is some probability of going perpendicularly. So when you have anyway gamma is 1, it doesn't matter when you reach the goal. All that you want is you want to reach the goal, right? So why do you want to take this risk of falling into the hole, right? If you there is some probability of falling into the hole, so you will there is in the expected reward will decrease. But if you go into this wall, then either you go up or go down. If you go up, you'll reach the goal, like by going right here. If you go here, you can again come back like this. So, eh, because irrespective of when you reach the goal, you are going to get plus one. But if you fall into the hole, you are taking a risk of falling into the hole, and your episode will terminate with a minus one reward. So here, playing safe is the best thing to do. At any cost, you try to like avoid falling into the hole. But if my gamma was not equal to 1, then maybe it's worth taking a risk at some gamma. Right? If gamma is, let's say, uh, very small, let's say gamma is, let's say, 10.1, then if I reach the goal after a lot of time, the return that I'll get will be zero point 0.1 power, let's say 100, which is not much. Maybe it's worth taking a risk, and with some probability you'll fall into the hole, but with some probability you'll go here. So the expected reward might be much better than this. The expected return might be much better than this. So depending on your gamma, maybe at some threshold gamma, uh, you might change this action to this action as the optimal action. If gamma equal to 1, then there is no point of taking any risk at all. If gamma is very small, then you have to absolutely take the risk. Because after, let's say gamma is, let's say 10 power minus 6, what is there? If you don't go in one or two steps, then you don't get anything, right? So that is changing the MDP structure, right? Here we are just talking about a parameter in the MDP. We are not changing anything about the MDP. I'm just changing the constant gamma. Okay, so what's the question? Yeah, that is also similar to this having gamma less than 1. Like, I think in the third question was telling that, right? Either you can have zero reward everywhere. In the terminal state, you can have plus 1 and choose a gamma less than 1. That is also fine. The other way is you just give a minus 1 reward for every transition that you make. Those are two ways of encouraging shortest path. Mm. The other one, two copies. You maintain V pi old, V pi new, and just calculate V pi new based on V pi old. Yeah, because that is what the definition, right? Because the normal thing is a mapping from Rn to Rn, right? You take an input vector Rn, you get another vector Rn. That's how we showed the contraction mapping also, if you remember, right? Like you're taking Bellman expectation is like an operator function which takes in your current value, like say value function, and it will give you another value. Hmm. I think similarly we have to show that the maybe there are some. I think I thought that once. Maybe I'll give you. Just send me a mail. I'll send you a video recording which discusses that proof. I don't remember. I think I thought that once, or there is an NPTEL course by Professor Balaraman Ravindran at IIT Madras. He teaches reinforcement learning. No, I don't remember the proof right now. Yeah. But I think that video course has that NPTEL course on reinforcement learning by Professor Ravindran. He has that lecture, I guess. You can try to see in that. No, synchronous iteration means like you are having that Bellman expectation update, right? So that one will be like you calculate V pi in terms of V pi, right? So what is it? V pi of like you write V pi in terms of vector form, right? Bellman expectation. What is that equation? P pi equal to R pi plus gamma P pi V pi, right? This is a vector form, right? So synchronous means if you want to do this update, so how will you do? Generally, if you have A equal to A plus 1 kind of thing, what will you do? Uh, like You have to. So this is just like you have some vector here. You need that whole vector to find this new vector, right? So that's all I'm saying. Like you just think of it as v new equal to r pi plus gamma p pi v old. So v old is the old copy of the vector. V new is the new copy of this vector. So you just maintain two copies and do this update. And then in the code you just write after this you just make v old equal to v new. Yeah, this is the normal. Synchronous thing is the default one. Like in place dp means you don't do it in vector form. You just do it in the scalar form. V pi of s equal to this thing. You just write it like this. R pi s plus gamma sigma s dash p pi s s dash v pi s dash. Something you'll write like this. So when calculating some value v pi s, you use all other states values, right? So you just use like if you do this for all the states once, that is equivalent to doing this equation, right? This vector equation. So if you in this place, if you use the old values, that is synchronous thing. So as and when you update one state, if you keep using that new v of s dash is to update the next state, that is called in place dp. Hmm. Any other doubts in the midsem? Okay, maybe you have some doubt in the second quiz. Okay. So maybe first I'll see the question. So which question are you talking about? Okay. So write the update equation of n step td for n equal to 2. Huh? Considering td lambda for lambda belongs to 0, 1, is it true that one step return always gets assigned the maximum weight? Explain. Okay. So the question is in td lambda, what is td lambda? If you remember, like we have, let me show you that. So we have for every n, we can have a GTN, right? So for if you do one step TD, then that will be what? If you do one step TD, that will be this, right? This is your GT1, right? So what is your GT2? GT GT2 will be RT plus 1 plus gamma times RT plus 2 plus gamma square times V of ST plus 2, right? This is your GT2. So what is TD lambda? Like you have such things from GT1 to GT infinity. You have GT infinity is like GT itself, right? GT infinity will be GT, right? Because RT plus 1 plus gamma times RT plus 2 plus so on. That is nothing but your GT itself. So you have GT1 to GT infinity. So what is GT lambda? GT lambda is a weighted combination of all these GTs, right? So for every GT, you are giving some weight and calculating the GT lambda. So the weights are given like this, right? Where is that? Shit. So in the so can someone remind me what are the weights we were giving for GT lambda? 1 minus lambda for the GT1, no? Okay, 1 minus lambda for GT1 and 1 minus lambda into lambda for GT2. Is that correct? So on, right? So your total weights will be 1 minus lambda by 1 minus lambda, which will be 1. Okay. Hmm? Okay. So if you take lambda equal to 1, what is your one step weight? Lambda is anything between 0 and 1, right? If you take lambda very close to 1, your one step return will be having lesser weightage, right? Now, how will it be higher? The total weight should sum to 1, right? Like if you take lambda equal to, let's say, 0.99, your one step return will be 0.01. This is your weight. What will be your two step weight? 0.01 into 0.99. Okay. Okay. So what? Oh no, one step doesn't necessarily get the same value. So is 1 minus lambda for one step return only? Are you sure in that formula? Okay. And the termination is also important, right? Like it's not that the second step will always have 1 minus lambda into lambda. Like if you have, let's say, the episode terminates in three steps, right? What is the weight for the last step that you give? You won't give some, let's say the episode terminated in two steps. Okay. This is your current step weight. The next step weight won't be this. It will be, there will be some correction which you will give at the termination step. And for the nth state, you will have follow 1 minus all the remaining things. So maybe I did not explicitly emphasize that. But otherwise, they won't sum to 1, right? So if the episode terminates in only two steps, then you will have 1 minus lambda and lambda. Like if the episode terminates in two steps, then you'll have this as the weight. So that does that mean either the first step or the last step will be the highest? Other steps are you are multiplying with some number between 0 and 1. So it will be definitely smaller than the first one. Either the first one will be the highest or the last one will be the highest. Okay. Yeah. Um, any other questions? Do we know the MDP or not? Like you can apply that in both the cases. Like generalized policy iteration is just means that you are not evaluating the policy fully. You are approximately evaluating it. And while improving the policy, also you are not being greedy. You can be epsilon greedy or something. So both these steps, like there are mainly two things, right? You start with some policy pi naught, and you evaluate the policy. So you'll get v pi naught. Then you improve the policy, you will get pi one, right? So generalized policy iteration means you don't fully evaluate policy pi naught. You just roughly evaluate what is v pi naught. So through Monte Carlo, etc., that is what we are doing, right? We are roughly estimating what is v pi naught, or so that we can do either in the model when you have the model or when you don't have it. That is one approximation. The other approximation, instead of being greedy with respect to your current policy, you can approximately improve the policy. Like if you are greedy, then the policy improvement theorem guarantees that you will fully improve. Like epsilon greedy is like you are not doing the exact policy improvement, you are roughly improving. Yeah, just to have enough exploration. Yeah, any behavioral policy which ensures that yeah, which ensures that all state action pairs are visited often. Like every state action pair should have a non-zero probability of visiting. Yeah, even if you use random policy, that's fine. It's just Q learning, like the value iteration. It's just value iteration algorithm. What you have to do is you have to keep updating the state action pairs of all possible state action pairs. If you update them enough number of times using that equation, then you are fine. So to just make sure that you are updating all possible state action pairs, you can either behave randomly, but the convergence rate might vary. If you behave randomly, maybe it will take longer time to reach Q star. If you behave maybe epsilon greedy with respect to your current Q, maybe that will take you have a different convergence rate, but it will definitely converge to Q star. No, like in the book which we have seen, we are using epsilon greedy policy as a behavioral policy, right? With respect to our current Q estimate, whatever you have. So currently, if you have some Q, which is an approximation, right? You are maintaining a Q table, right? So you're taking your policy to be argmax over a Q of S comma A. This will be your A star. You are behaving according to this A star with probability 1 minus epsilon, and with some probability epsilon, you are taking random action. That's what I mean by behaving epsilon greedy with respect to current Q. Because Q is something which you are estimating. At a Q star, current Q is an estimate of Q star, right? Yeah. So that's what we are estimating, right? Your Q only will converge to Q star, right? Your estimate of Q star, this is your estimate of Q star, which you will keep updating. Finally, it will converge to Q star. So your current iterate, if you behave epsilon greedy with respect to that, that's what the algorithm tells in the book. Yeah, yeah. So I haven't covered explicitly the class, like backup diagram I briefly introduced. This time I did not emphasize so much. So, but the thing is, let's say you have at some state there are multiple actions that are possible, and every action might lead to, let's say, a couple of states, right? So in the let's say Bellman expectation equation, what do we do? Like this is V pi of s, and we'll write V pi of s equal to R pi s plus gamma times sigma s dash p pi ss dash into V pi of s dash, right? Here you are looking at all possible s dashes and then taking the decision, like updating your V pi. So that is like a full width backup. You are looking at all possible things, and this will also depend on all possible actions, right? R pi s is what? RSA pi of A given as sigma over A. This is R pi s, right? If you follow a policy pi, what is the expected reward, immediate reward that you'll get? Which is RSA into probability, expected RSA, if you follow policy pi. So you're looking at all possible actions to compute this and all possible states to compute this. So this is called full width backup. Based on all possible actions and all possible states, you are computing your V pi. In the SARSA, what we are doing is you are at some state S. You will take one action according to you are in some state S. You will take AT sampled according to pi. So there might be three actions that are possible actually. There are three actions that are possible, but we'll just sample one action based on our policy and we act according to that. Then the environment will, like, let's say you took this action. Now there are two possible next states, let's say. The environment will pick one of these two states and give you, right? So that will be your ST plus 1. So this is like a sampled version of this state. Here there are so many branches which are possible. You are sampling according to pi one action, and the environment is sampling one state, next state according to the environment dynamics. So that's why it's called sampled backup. This is called full width backup. So you're considering all the branches and then making this update. In Sarsa, we'll just make the update like this, right? V of st equal to rt plus 1, like we knew all that we'll write, but main thing we'll write is this, right? V of st plus 1. So instead of summing over all possible states, you are just taking st plus 1. Instead of summing over all possible actions, you are just taking rt plus rt plus. So this is called the sampled update. This is called the full width update. Um, any other questions? Can you repeat your question? In off policy Monte Carlo. Yeah, so we have, let's say, rho is the, so let's say mu is the behavioral policy. Let's say pi is the target policy. What are you saying? Hmm. Will depend on the policy. No, you can think in multiple ways. So, for example, let's say you want to estimate what is V pi for some policy pi. Okay. Now, one way is you start behaving according to policy pi and generate lot of episodes and get GTs and take the average of all those GTs to get your estimate of V pi. That is the straightforward way, right? You act according to pi, you get some GTs, take the average of those GTs, that will give you V pi of S. Expect like some estimate of V pi. The other question is, now let's say you have done this for some policy pi. You have done all this for some policy pi. Now you have got some lot of data which you behaved according to pi. Now someone comes to you and says, can you estimate some other policy, like let's say V, like let's say some other policy V pi 2. I will give you some policy pi 2. Now one way is you again start interacting with the environment according to pi 2 and then get GTs and take the average of them. That is on policy. Let's say you don't have the access to the environment anymore. Let's say someone gave you the device, you tried some policies, you estimated them, and you collected some data. Now the device is taken away from you. Now someone asks you, can you estimate V pi 2? Then you have to use the old data only, which you have with pi. With policy pi, you have some episodes. But using those episodes, you have to estimate what is V pi 2. You are not allowed to take any more actions according to pi 2. You don't have access to the environment now. No, MDP has nothing to do with pi 2, right? Hmm. Hmm. Probability of action. Hmm. Okay. So that we have, right? We know what is pi 2. Pi 2 is what? This we know for all possible S, A. Policy is something which policy specifies this, right? What is policy? Policy tells you if you are in some state with what probability you should take what actions. This is given by the user to you. The user tells you this distribution. Now he's asking, I give you this pi 2, which is for every state, I'll tell you what probability you should take what action. That is the policy. He specifies you the policy. Now he's asking what is V pi 2. So this you know. This is given to you. What do you mean? In what context you're talking about? No, target policy is something which you are interested in. Like, for example, if you are finding V pi for some in the prediction problem, there is nothing called optimal policy, right? You have some policy pi, you want to estimate what is V pi. So there also we call it target policy. So you behave according to pi, but you estimate what is V pi 2, let's say. That means your target policy is pi 2. Whether it's optimal or not, we don't care. We are just interested in finding what is V pi 2, but you behaved according to pi. And in the Q learning and the optimal policy learning, one of the conditions that I mentioned is your target policy should converge to the greedy policy in the limit. If you remember, I have given this condition, Glee conditions, right? Greedy in the limit with infinite exploration. So maybe that's what you're asking. The target policy should become greedy in the limit. Like if you're changing the target policy in SARSA, your target policy is an epsilon greedy policy. Your behavioral policy is also same policy because SARSA is a non-policy algorithm. So there, if you want to converge to the pi star, then your target policy should become greedy in the limit. That is, your epsilon should decrease with, let's say, 1 by t or something like that. And your behavioral policy should have infinite exploration. That is, every action, like for any algorithm which is using, let's say, TD based method, like even Q learning is using TD based approach, right? For any TD based approach, if it has to converge to pi star, these are the two things which are required. So even for Q learning, you need infinite exploration, and your target policy should become greedy in the limit. So in Q learning, at every time we are behaving greedily, right? We are updating the policy greedily, which is what RT plus 1 plus gamma times maths over A Q of S comma A. That's what we are doing, right? So this is the greedy policy. Which step we want to update Q of S comma A? That we are behaving, like as I said, in uniform random policy also you can do for the behavioral policy. You keep behaving uniformly. You start from some initial state, you take a random action, it will take you somewhere. Again, you take a random action, it will take you somewhere. You keep following this, and whatever you follow, you will keep updating this, right? Q of STAT. So that means what state actions you are updating the Q function. You are updating the Q functions for whatever states you are visiting, right? So that means whatever behavioral policy is determining what states you visit, right? So that means if you visit all possible states and actions, you will update all possible values in the table. You are maintaining a Q table, right? So when will you update some entity in the Q table? When you visit that state action pair. So that means if you want to, otherwise some values in the table will become stale if you never update them, right? Then it won't be, how will it converge to Q star if you're not updating them? So all that you want is you want all state action pairs to be updated a lot of times. For that, you have to visit all state action pairs a lot of times because you are updating some value in the table only whenever you visit that state. So if your behavioral policy ensures that you visit all possible states and take all possible actions in those states, then your Q table will keep getting updated. So that's what I mean by infinite exploration. Yeah, this is already taken care. In SARSA, what are we doing? We are following epsilon greedy policy, right? So your RT plus 1 plus gamma times Q of ST plus 1 comma AT plus 1, right? This is the SARSA update. What is AT plus 1? AT plus 1 is epsilon greedy with respect to your current Q, right? So AT plus 1 is epsilon greedy. Here you are being greedy. In Q learning, in epsilon SARSA, you are using AT plus 1. AT plus 1 is chosen according to your behavioral policy, right? There it's both the same, right? Behavioral policy and if you want convergence in SARSA, you want both these things because both are same. You want this 80 plus 1 to be chosen according to greedy policy in the limit at least. Otherwise, you are not doing a greedy update. Like your target policy is not greedy. Otherwise, you do that. And also, you have to update all possible S, comma A's. So that's why your behavioral policy should be having infinite exploration. As long as you update all possible s, s in this table. Like if yeah, even SARSA will converge if you choose epsilon equal to 1 by t, but Q learning will converge irrespective of what epsilon is. Even if epsilon equal to zero point 0.1, Q learning will converge to the optimal policy, but SARSA will not converge if you take epsilon equal to zero point 0.1. SARSA will converge to some epsilons of the policy. No, that is you are using some instead of. I think one question was there in the forums, right? Can you explain how Monte Carlo boils down to alpha? We are doing right. So this alpha t should have that property that it should sum to infinite, and this should be less than infinite. If you don't satisfy this, you won't. That convergence is not guaranteed. Yeah, the like it might converge to something, it might not converge to the optimal policy. Yeah, yeah, yeah. For Lee and this one, these two conditions. So these are some conditions which you will find everywhere, even in your standard gradient descent algorithm. You will, if you want convergence to the local minimum or even anything, it's you need this kind of a guarantee. Even for everything, like wherever you're using that small constant alpha, if you want, even in the prediction problem, let's say you are interested in finding v pi of s, you are using, let's say, Monte Carlo based prediction. Even further to converge, you need these conditions. So these are some standard conditions which you'll need wherever you use alphas. No, like in the tabular setting you're asking. Always converge means under, you mean if you don't satisfy these things, if you don't satisfy Glee property. I don't know about that. No, it should not have converge means it might converge in some cases, it might not converge in some cases. That doesn't mean you can say it will converge, right? Like when you say it will converge, it should converge in all cases. Even if some cases, if it doesn't converge, you can say it, in general it won't converge. Yeah. No, even if you don't satisfy these properties, sometimes it might converge, but that doesn't mean it for every MDP it will converge. No, for example, if I take a random number, if you ask me whether it will be less than 100 or not, sometimes it might be correct, right? I cannot guarantee that whatever random number you take, it will always be greater than 100. If I ask you, give me a proof that it will always be less than 100, you'll say it won't be true. But that doesn't mean it will never occur, right? It will converge to the best policy among epsilons of policies. Like, for example, we have seen that in the assignment 2 part B, right? It was converging to a safer policy. Like in that cliff problem, if you remember, like the Q learning was converging to this policy and the SARSA was converging to this policy, which is a safer policy. So that's not the best policy, but it's the optimal policy among all policies which will explore with certain property. Because if you are constrained to always explore, then if you follow this policy, that is more worse, right? There is a probability of falling into the cliff, high probability of falling into the cliff. So if you look at all possible paths, which will keep exploring randomly with some probability, then this is the best policy because it's playing safely. So that is what I mean by it will still converge to the best policy, but it's not the optimal policy. It's the best policy among all epsilons of policies. Epsilons of policy means a policy which will explore at least with probability epsilon. Okay, maybe we'll wind up here. Maybe the people will come to close the room. Maybe we can discuss outside if there are any other questions. I don't remember. Like I have given some sections, right? Just practice the questions related to those sections. Like in every notes, I have given some references in the bottom, right? You have to just see those questions. I don't have any such list of questions which like